Okay, so in these next few lectures, we're going to talk a little bit about fish condition. And we'll talk about what do I mean by condition. And then one of the first measures of condition was Fulton's K. Then we'll spend a lot of time on relative weight, which is the common one we use today. And then we'll wrap it up by briefly mentioning some other condition indices. Okay, well, if you recall from our previous work, we looked at the relationship between length and weight, and we summarized that by a curve that is a power equation. And looking at this relationship between length and weight is what we are doing when we're looking at fish condition. Basically, it's a measure of how healthy the fish is. It's in general a measure of plumpness. So you have two fish that are the same length, they can have very different weights. And if you have one that's getting better food, or the habitat's better, the water quality's better, or it's got less disease, it's going to be heavier at a given length. It's going to be more plump, and it's going to be in better condition. Well, by studying condition, we can understand a lot about what's going on in our fish population. So what we're looking for here is a number, and each fish will get a number, and if the number's bigger, that fish is in better condition, and if the fish is in worse condition, that number will get smaller. So what we're going to do for this first one is we're going to modify the length-weight relationship, and that's going to give us an equation that we can use as an index of condition. And so this is our original length-weight relationship, and we just rearrange it so that we can say that A equals the weight divided by length to the B. And now we just change a few of the variable names. Instead of A, we're going to use K. We're going to assume that B equals 3, which is what we call the isometric growth. And then we're just going to add a scaling factor just so these numbers are somewhere around 1 and they're easier to report. And so if you look at that, what we have on the right there is called Fulton's K. And the scaling factor is different whether you're using English or metric units. This is for metric units. And this is one of the first condition indices, and a lot of the older literature you're going to see that they've used Fulton's K. And so it's pretty simple. For each fish, you have a length and a weight. And so you plug the fish's weight and its length into this equation, you get a value for K, and that'll tell you the relative plumpness of the fish. And so if we do this for a bunch of fish, then we can get some insight into our fish population. And of course, if you've got two fish that are the same length, the heavier one's going to have a higher value of K. It's more plump and it's in better condition. And like I said, this will give us insights into the health and the food supply and things like that. And so if you look at some simple examples here, you can see you've got two lakes, and we've got 4 fish in each lake, and they're all the same size from each length. We've got 100 millimeter up to 225 millimeter. And in one lake, the fish are relatively heavier at each length compared to the other one, and you can see the value for Fulton's K in that third column. And so at any length, the heavier fish has a higher value because it's in better condition. And you can see how Fulton's K is, around 1 because of that scaling factor. So this is not used as much anymore because it's got a few problems. One, you can't really compare it between two different species. Different species have different body shapes, so K is often not comparable. So for example, a largemouth whose Fulton's index is 1.5 is not necessarily in the same condition as a bluegill that has K equals 1.5. Another big problem with Fulton's K is that it's length biased. And what that means is that we consistently get higher condition for longer fish even though they're not more relatively plump. This happens because you'll recall we assumed that B equals 3. often that value of B is greater than 3. So the fish naturally put on weight a little faster than the cube of the length. But if you compare them, if you assume that the growth is isometric, then it looks like your longer fish are always going to be in better condition, and we don't want that. And so we need a better condition index, and that's where relative weight comes in. Okay, most people use relative weight as their index of condition these days. And there's a couple of reasons. Basically, it solves the two biggest problems with Fulton's K. So now we can compare relative weights across species. And it does not have a length bias like Fulton's K does. And so how does this work? We start with what's known as a standard weight. And what do you mean by a standard weight? Well, for a given species at a given length, we define how much a healthy fish should weigh, okay? And you say, well, what does healthy mean? Well, healthy can mean a lot of things, but the important thing is that we define this standard to be an above average or a relatively healthy fish at every single length. So, for example, a 200 millimeter largemouth bass should weigh about 106.2 grams if it is a healthy fish. Well, the obvious question is, well, who decides that? How do we define what a standard weight is at any length? So how much should a healthy fish weigh at any length for a given species? And the way we do this is there's one equation published for each species. And so somebody has to go out and do the math and figure out this equation. And not all species have them, but all common species do, and we're adding to this every day. This equation is based on a very large data set spread across a very large geographic region like North America, or probably more importantly, across the species' entire range. So we look at fish across their entire range and across their range of sizes, from very small to the very large, and we look at the relationship of length to weight across all these studies. And from that, we get a single equation, and that equation allows us to plug in a length, and the equation spits out the standard weight for that length based on all the data we have on that species. And so we call the standard weight, we signify it as W sub S. And what this is, this represents the 75th percentile weight for a given length. So the standard weight is not the average fish, but an above average fish. So a relatively healthy fish that's at the 75th percentile of weights for its length. And again, that's based upon very large data sets. So let's look at a handout here to give you an idea of what I mean by the 75th percentile. So you look here, this is handout number 7, just trying to demonstrate what the 75th percentile weight looks like. So this is just some data, and what we're looking at is we've got 3 columns here. The first column, the fish are 50 millimeters long. In the second one, they're 100 millimeters, and in the third, they're 150 millimeters long. And this is, each of these columns has 100 fish in it, and they're all the same length, but they all vary in weight. So this is like we took a sample of 100 fish at each length from all over the country, from a wide range. And you can see that although they have the same length within a column, there's quite a bit of variability in weight. And that's what you would expect with fish. And some are going to be very light and some are going to be very heavy. And we're going to use this to help define what our standard weight is. So if we look at this first column of the 50 millimeter fish, and we have them arranged from the lightest fish to the heaviest fish. And so this sort of represents the range of weights you would expect for a 50 millimeter fish of this species. This is made up data, but you get the idea. If we look, the average weight for a 50 millimeter fish is 25 grams. That's the average of this weight column. But we want to look at the 75th percentile. That's going to be the 75th fish in this list. Why? Because I have 100 fish. And so the 75th percentile is the 75th largest weight. You don't have to have 100. You know, it's always, you can do this on any number of fish, but I'm just doing this just to make it easy to understand. So I've got 100 fish. The 75th largest weight is 30.2. That's the 75th percentile for the 50 millimeter fish. And you see that that's greater than average. So again, this is a fish that is relatively healthy. Well, we can continue that logic then with the other columns. If we look at the 100 millimeter fish, we've got all the possible weights. The 75th percentile weight for that length fish is 73.6, which is greater than the average of 66.2. And finally, if we look at the 150 millimeter fish, their average is 111 grams. The 75th percentile weight for that length is 117. So essentially what you would do is collect such data across all lengths that you could find across a wide range, and then you would look at the 75th percentile of every length. Usually you would do something like every 5 millimeters or something like that. And once you have that, then you just simply fit a regression line to these data. You've got a length and a weight, and here you've got a length and a weight, and here you've got a length and a weight. You take all those lengths and weights and you do like we did before. You make a length-weight regression. That is how you get the standard length, and that is how it represents a relatively healthy fish. Okay, so from that, you see now what I'm talking about. If we got all the, for example, 100 millimeter largemouth bass in North America, they would have a range of weights, and we could arrange them from the lightest weight to the greatest weight, and we could pick out the 75th percentile, and that's what we base our standard weight on. And this represents a healthy or a plump fish, not an average fish. And so the equations that are published allow us to take any length and get the standard weight, the 75th percentile weight for that species at that length. And that's what W sub S is. Okay, and so that then is how do we use this equation, or how do we publish these values? Well, that equation is in this form, and this should look familiar because this is the log transformed version of the length weight regression that we were just talking about. We just talked about it with Fulton's K. In a previous lecture, we talked about the relationship between length and weight. And so here you've got the base 10 log of the standard weight equals A plus B times the base 10 log of the total length. And so what's published are these values of A and B. They're unique for each species, and this allows you then to take the length of your species, you plug it into this, and it'll give you the standard weight. And that standard weight, again, is the 75th percentile based upon a wide range of observations. And so here are some of the values that are published in Fisheries Techniques, and I gave you a handout on this. And actually I see that the handout number is incorrect on the slide, but you get the idea. And so here, for each species, you see the value of A, and that's different whether or not you're working in English or metric units. And then it also gives the slope of that log transform line, and that's always the same no matter what, whether you're in English or metric units. And so for your species, you go look up the value of A, the value of B. That gives you the equation. You plug each fish has a length, and that length is plugged into this equation to give the standard weight for that length. And that tells you how much a healthy fish should weigh. And so for example, here we're going to do a 200 millimeter largemouth bass. There's the log transformed equation. Where do I get the values of A equals negative 5.316 and B equals 3.191? That's from that table. That's someone looked at a bunch of data, figured out that this is the 75th percentile weight at each length, and everybody uses the same ones. That way everybody is comparing to the same standard. You'll notice here that the value of B is a little bit greater than 3, which is what we said earlier, that most of our fish species have allometric growth, positive allometric growth, where they grow a little bit faster than the cube of length. And so if I got a 200 millimeter largemouth bass, I just plug that in. And I solve for W sub S. And so that tells me that a 200 millimeter largemouth bass that is relatively healthy should be about 106.2 grams. And that is my standard, and that is your standard, and that is everybody's standard who works with largemouth bass. And that 106 grams for a 200 millimeter bass, again, is not the average size of a 200 millimeter bass. It's an above average, a relatively plump fish. Another way to look at that is to say, of all the 200 millimeter largemouth bass in North America, about 75% of them are below 106.2 grams. Just saying the same thing differently. Okay, so that tells us for every fish how much it should weigh if it's healthy. But of course we weigh each one of the fish as well as take their length, so we can look at how much it actually does weigh, and we can compare what it does weigh to what it should weigh, and that gives us a relative weight. And so that's the essence of the relative weight. It's relative to this standard that everybody uses, and that standard is a relatively healthy fish. Another way to look at this is, how is the weight of each fish relative to the average fish of the same, an above average fish of the same length. And so if the actual weight of the fish is less than the standard weight, we say that fish is in poor condition. And of course, if it's greater than that standard length, we say the fish is in good condition. And that's the basic idea of relative weight. So again, why do we go to all this trouble? It's better than Fulton's K. We can compare it across species. There's no length bias. And this is sort of the de facto standard that people use in fishery science these days. So next we're going to step through some actual calculations and practice this a little bit. So let's see how we're going to calculate some of these. I showed you how to calculate the standard weight for any length, but we want the relative weight for each fish. And here is the equation for the relative weight. So W sub R is the relative weight. This is the actual index of condition. W sub A is the actual weight of the fish. And of course, W sub S is the standard weight that we just got from the equation. So if you look at this, you can see that relative weight is simply the actual weight of the fish as a percentage of the standard weight. And so if you are in good condition and your fish is above the standard, it's going to be over 100, and if it's below the standard weight, it's going to be under 100. And so let's say that I get a fish, a largemouth bass, and it's 200 millimeters, and it weighs 100 grams. What's its relative weight? Okay, well, first step, you got to find the standard weight equation for largemouth bass. We saw that earlier, but you got to look this up if you're just starting. Most of the common ones are easy to find in the literature. Of course, I gave you a handout with all the more common species. Realize that we only use this for larger fish. Every species has minimum length requirements. And that's because there's a lot of variability at small sizes for fish. Plus, often your smaller fish, they don't weigh as much, and a lot of times your balance or your scale does not have enough precision to properly measure small fish. So always pay attention to the minimum length requirements and don't use this for fish below those requirements. And again, this standard equation is in logarithmic form, so you have to transform from base 10 logs back to whole numbers. So this is what we did before. We took our standard, we took the length of the fish, which this fish is 200 millimeters. Here is our largemouth bass standard weight equation. I first take the log of the standard length, and this is the base 10 log, excuse me, I take the base 10 log of the fish's length, and then when I plug that in, I end up seeing that the log of the standard weight is equal to 2.026 in this example. And so I need to take the anti-log to actually get the value of the standard weight. And some calculators have anti-log, but remember how base 10 logs work. If you've got the base 10 log of W sub s equals 2.026, that means that 10 to the 2.026 equals W sub s. This is important to know because if you're doing this in Excel, Excel does not have an anti-log function. But all you got to do in Excel is raise 10 to the power of the value that you have, and that is how you take the anti-log. And so in Excel, we would just take 10 and raise it to the 2.026, and that gives us the standard weight, which in this instance is 106.2. Now that we've got the standard weight for that length, we compare the actual weight to that standard weight. And remember, in this example, our actual weight is 100 grams. That's W sub A. And so we divide the actual weight by the standard weight and multiply by 100. And so in this example, we see that this fish has a relative weight of 94. So it's relatively skinny. It's in relatively poor condition. And this makes sense if you think about it. 100 grams is less than the standard weight. This fish is 94% of the standard weight for fish of its size. And so our fish is relatively skinny. It's only 94% of the standard weight. And so that is the way we do these calculations. And next we're going to talk about how do we report them, because once we do all these calculations, reporting them and graphing them is where you really get the information that you want from this index. All right, now we have a relative weight for every fish in our sample. Let's see how we're going to report this. Now, it's not useful to report just the average relative weight. We usually do report the average relative weight, but that by itself does not give you enough information, and you can really get a lot more utility out of the relative weight by graphing it in a couple different ways. The most common way is to plot relative weight against the length of the fish, and this will look and give you important trends that will help you understand your fish population. So here's an example of largemouth bass that were taken from a particular lake. And you can see that on the x-axis we've got the total length, and for each fish we plot its relative weight against total length. And relative weight is on the y-axis. Now we have created a horizontal line at relative weight equals 100 because that's our standard we're comparing to. And that way you can sort of see the condition of each fish relative to the standard. And so fish that are above this line are in good condition, and fish that are below the line are in bad condition or worse condition. And in general, for most fish populations that are being managed, you're shooting for a relative weight in the range of 90 to 110. You want most of your fish to be near this 75th percentile standard. You'll also note that we do report the average relative weight here, which is 107, which tells us overall these fish are relatively plump and they're in pretty good condition. Now, you didn't see many patterns in that previous graph, but this graph illustrates the utility of plotting relative weight against a different value. In this one, we're plotting relative weight versus age. And sometimes this can be very similar because the older fish are also the longer fish. In this particular example, these are crappie that were stunted, so all these crappie were the same length. But when we look at the plot of relative weight against age, you see a very clear downward trend. And you see the average relative weight is 77. So these fish in general were in poor condition, and I don't know if there's any of them that are above 100 relative weight. And this is how we can get some information. We can see that the older the fish, the worse condition they're in. Remember, all these fish were about the same size. That suggests to us that the older fish are, as they age, they just are less healthy and they're doing less well, and they're certainly not in as good a condition. Now, when we're looking at relative weights, and if we have, we're trying to decide what's driving the relative weights, the most likely influence is the food source. So whenever you're trying to explain a trend in relative weights, you always start by talking food source. And relative weight has been correlated with things like fat reserves, and so there's good experimental reasons and good data to suggest this is the truth, but this is usually how these things are interpreted. And so if you got fish that are in poor condition, that suggests that they're not getting enough to eat. There's probably not a vulnerable forage for them, or intraspecific competition, or some kind of competition is high. For some reason, these fish are not getting enough to eat, and that's why they're in poor condition. And of course, the fatties, the ones that are in good condition, are getting more to eat for one reason or another. Of course, then other things that we always talk about are things like water quality and true health or disease, parasite load, things like that. These are also factors that could influence the condition of a fish. But let's always first start by looking at the food supply. And so here's an example of a channel catfish from 2 pools in the upper Mississippi River. And so these fish were caught on either side of Lock and Dam 19. And again, we're plotting relative weight across total length. And you don't see much of a pattern above 175 millimeters. But you see a very clear trend at these smaller fish. And so, for whatever reason, these smaller fish have a ton of food. Well, they're probably eating something different. They're probably not food limited. This deserves further investigation, but they're fatties, whereas the larger and the adult fish are There's no real trend, and they're all kind of clustered around the 100 line, and so they're still in pretty good condition, but these younger ones are obviously in great condition. And that's one of the ways that we use this relative weight in order to understand our fish population. And here we go back to my crappie and the relative weight versus age, and this is just reiterating what I said earlier. They were all the same length, so they all likely have the same available forage. So this would be a situation where you say, well, maybe it's something other than forage that's driving that condition factor, because they all were from the same pond and they all should have the same forage because they're all about the same size. Now maybe the older ones are not as good at catching the forage. That could be something, but it could indicate just the relative effects of aging, and that older fish don't grow as well and they're in worse condition. And so that is relative weight and how we calculate it and how we report it, and that's the one we're going to use the most. In the last little section, I'm just going to quickly talk about some other condition indices that pop up and different ways that we can use those. So in this last segment, I just want to introduce a couple of other condition indices you may run into. Of course, these two are the most common, and relative weight these days is used more than Fulton's K. But we do have some others. One that's interesting is the RNA to DNA ratio. This is not as common, but it's an interesting idea. So if you think about any organism, think about a fish, how many copies of DNA does each cell have? It has one copy, right? How many copies of RNA does it have per cell? Well, that depends. I mean, you only get RNA if a gene gets transcribed, but of course genes can get transcribed over and over again. So you can have one gene, but many copies of RNA for that gene. And if the fish is growing, then they're going to be making multiple copies of a lot of genes, but they're going to be making multiple copies of RNA from each gene because they're trying to make a lot of protein. Remember that fish are mostly protein, but in general, you know, if a fish is growing, if their cellular metabolism is cranked up, they need to be transcribing a lot of genes. And so if you look at the relative amount of RNA per DNA, that can give you an indication if the fish is in an active growth phase. And so if you're growing and if you're in better condition, you should have more RNA per DNA molecule because you're transcribing each gene multiple times. Don't see this a lot, but I think it's a very good idea. And I think this probably has the advantage that you can get fairly precise with this. One that is more common that you'll see, and a lot of times you'll see this in relation to studies that are looking at the actual health, like say things like the parasite load, is the liver somatic index. And you see that word somatic, you start thinking body. This is also called the hepatosomatic index, so the LSI or the HSI. And this looks at the liver as a percentage of the non-gonad body weight. So that body weight is the somatic part. And this one is backwards from what we've used before. The healthier the fish, or the better the condition, the lower the LSI. And this is because if you're in poor health, then you tend to have a more fatty liver, or your liver is more swollen. Think of alcoholics that have cirrhosis of the liver. Their livers are abnormally big. And so if you have a fish that has an abnormally large liver, that fish is probably not in as good a condition, and so their LSI will be higher. The most common of these that you run into is the gonatosomatic index. And so we've got somatic again. We're talking about body and gonads. Call this the GSI. And this is simply the weight of the gonads as a percentage of the weight of the fish. And when we do it, we always do it as a percentage of the non-gonad weight. Some people do it as a percent of the total weight, including the gonads. It doesn't matter because you're looking at trends one way or the other. And this is expected to climb as the fish get closer and closer to their spawning date, and then rapidly drop off. Especially in the females. If you think about a female, she's going to be putting on more and more eggs, and the eggs are going to get bigger and bigger. And so the egg mass as a percent of her body weight is going to get bigger and bigger, and then she spawns and she's going to lose a tremendous amount of weight overnight. And so if you look for that knife edge drop off in GSI, that can clue you in as to when the fish spawn, which is what I'm saying right here. And this also works for the males because the males are also going to release a lot of gonads, a lot of gametes into the water. And also, you know, once everything's done spawning, the fish tend to not put as much energy into producing gametes. But then over time, their gametes again start to climb, you know, if they spawn multiple times. And here's an example from a study we did with oriental weatherfish, which is an invasive species up by Chicago. And the blue is the mean GSI for the females, and the maroon is the mean GSI for the males. And months are the numerical months, so April, May, June, July, August. And you can see how in April, the female GSI is high, the highest we recorded. And then in the next month, it's dropped off quite a bit. And then you can see this slow increase as the summer progresses. And so to us, and we see somewhat similar pattern in the males too, although the males don't quite increase as the season progresses. Well, males can put on gonad weight very quickly. And so they might wait until just before it's time to spawn for their gonads to swell, but females might have to work on it. That's a speculation. But this to us suggests that these fish spawn sometime in April. That's the utility of the GSI, and of the ones I've talked about, this is the one that you're going to run into most commonly. Okay, so that is fish condition, and we're going to do a lot of calculations both in Excel and R, and practice on doing these different calculations. If you've got any questions, let me know. I'll talk to you later. See ya.